Which points on this string never move? The string is visibly oscillating, but the pattern isn't travelling anywhere. These points stay still. The three loops reverse simultaneously, with adjacent loops moving in opposite directions. This is a stationary wave, also called a standing wave. It is not a wave that is stopped. The medium is still moving, while the pattern stays in place. Start with a progressive wave travelling along the string. It reflects at the fixed end and returns with the same frequency and the same speed, but in the opposite direction. If the two waves have equal amplitudes, their displacement add to form a pure stationary wave. This point-by-point addition is called superposition. Where the two waves always arrive in antiphase, their displacements cancel. Those fixed points are nodes, and their displacement is always zero. Midway between adjacent nodes, the two waves arrive in phase and therefore they reinforce each other. We call these antinodes, where the resultant has its greatest amplitude. Watch the resultant through a complete cycle. Every loop passes through equilibrium at the same instant, and then adjacent loops reverse to opposite sides. The nodes never shift. What is stationary is the pattern of nodes, antinodes and amplitudes, not the string itself. The same superposition principles produce stationary patterns in strings, sound waves, and microwaves. One loop is half a wavelength, not one complete wavelength. Adjacent nodes are lambda over 2 apart. Adjacent antinodes are also lambda over 2 apart, and a node to the nearest antinode is lambda over 4. Here, adjacent nodes are 0.20 meters apart, so the wavelength of the travelling wave is twice that distant. 0.40 meters. The string is driven at 120 Hz, so V equals F lambda gives 48 meters per second. That is the speed of the two travelling waves which makes the pattern, not the transverse speed of one point on the string. Phase is also different from a progressive wave. Every non-node point between the same pair of nodes oscillates in phase, although its amplitude depends on position. Cross one node and the motion is in antiphase, a phase difference of pi radians. The node itself does not oscillate, so it's not useful to assign it a phase. An ideal stationary wave transfers no net energy along the string. Energy is exchanged between kinetic and elastic potential forms as the string oscillates, but there is no steady energy flow from one end to the other. A string fixed at both ends must have a node at each end. Only patterns with whole numbers of half wavelengths between those two ends satisfy that boundary condition. One loop is the first harmonic, with lambda 1 equals 2L. Two loops gives lambda 2 equal 2L, and 3 gives lambda 3 equal to 2L over 3. In general, n loops gives lambda n equal to 2L over n. If the wave speed is unchanged, Fn equals nf1. For our 0.60 meter string, the frequencies are 40, 80 and 120 Hz. The opening pattern was the third harmonic. For a stretch string, wave speed is the square root of tension divided by mass per unit length. Therefore, F1 is 1 over 2L multiplied by the square root of t over mu. Greater length or mass per unit length lowers the first harmonic frequency. Greater tension raises it. In the string practical, drive near the first harmonic, change one factor at a time, and retune to the maximum amplitude over one loop pattern. The equation predicts F1 proportional to 1 over L, proportional to the square root of t, and inversely proportional to the square root of mu. The full method belongs in the practical lesson. The same boundary argument works for an air column. These are air particle displacement diagrams, not the shape of the air. Ideally, an open end is a displacement antinode and a closed end is a node. A pipe open at both ends fits half a wavelength first and supports every harmonic. But if the pipe is closed at one end, it fits 1/4, then 3/4, then 5/4, so only odd harmonics occur. A pressure node occurs at a displacement antinode, and a pressure antinode occurs at a displacement node. In an exam, mark the boundaries first, count the half or quarter wavelengths, then use V equals F lambda. Next lesson we're going to look at refraction and total internal reflection.